NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor function equations using the definition. We will follow a precise 3-step algorithm and apply it to an example. We will now walk through a complete example, step by step. Solve the equation, floor of 2x minus 1 equals 4. We begin with the definition. If the floor of f of x equals n, then n is less than or equal to f of x, and f of x is less than n plus 1. Step 1. Identify the integer n. Here, the right side is 4, which is an integer, so n equals 4. Step 2. Apply the definition. Replace the floor with a double inequality using n equals 4. That gives 4 less than or equal to 2x minus 1, and 2x minus 1 is less than 5. Step 3. Solve the double inequality for x. First, add 1 to all 3 parts. Then, divide everything by 2 to isolate x. Let us visualize the solution on a number line. A closed point at 2.5 and an open point at 3, with the interval shaded in between. Therefore, the solution set is all x in the interval from 2.5, inclusive, up to 3, exclusive. We display the word example. Play button step 1. Apply the floor function property. We will show the property used. Then, we display the step heading. Quick challenge. Separate the integers from the floor brackets. Now, we rewrite each bracket using the rule. Play button step 2. Distribute the signs and simplify. We show a reminder to handle the negative sign correctly. Then the heading. Tip. Watch the minus sign before the third term. Now, write the expanded line with sign distribution. Play button step 3. Combine like terms. We recall that like terms can be added or subtracted. Then the heading. Combine the x terms and the constants. Play button step 4. Isolate the floor function. We add 4 to both sides to isolate the floor. Then the heading. Perform the operation to isolate the floor. Play button step 5. Solve for the interval of x using the definition of the floor function. We show the definition to convert floor to an inequality. Then the heading. Apply the definition with n equal to 6. Play button step 6. Express the final solution set. We display the step heading. Then the final answer in green with a celebratory moment. In this example, we solve a floor function equation step by step, and we will visualize the solution on a number line for strong intuition. Here is the problem we will solve. Step 1. We use a key property of nested floor expressions. The reminder says the repeated nesting of floor of x added n times equals n times the floor of x. Here, the nested part is 3x repeated 3 times, so the left-hand side becomes 3 times the floor of 3x. Step 2. We solve for the floor of 3x. Divide both sides by 3, and we get floor of 3x equals 9. Step 3. We turn the floor equation into an inequality using the definition of the floor function. If the floor of it equals an integer, I, then I is less than or equal to a, and it is less than I plus 1. Applying that with I equals 9 and it equals 3x, we get 9 is less than or equal to 3x, and 3x is less than 10. Step 4. Now, we solve the inequality for x by dividing everything by 3. That gives x is between 3 inclusive and 10 over 3 exclusive. In interval notation, that is the closed bracket at 3 and the open parenthesis at 10 over 3. To see the solution set clearly, let us draw a number line and highlight the interval from 3 to 10 over 3, including 3 and excluding 10 over 3. We mark the point at 3 with a filled dot and the point at 10 over 3 with an open circle. Then we shade the segment in between to show all the valid x values. A quick consistency check. Since the floor of 3x equals 9, we have 3x between 9 and 10. Dividing by 3 gives x between 3 and 10 over 3, exactly as our interval shows. Here is our example. We want to solve the equation. Floor of x squared plus floor of x squared plus floor of x squared in nested brackets equals 27. Step 1. Apply the nested floor property. The key fact is that when the same inside quantity repeats with floors, an integer contribution can be counted repeatedly. In our case, the inside quantity is x squared, and it appears 3 times. So the left side becomes 3 times the floor of x squared, and that equals 27. Step 2. Solve for the floor of x squared by dividing both sides by 3. That gives the floor of x squared equals 9. Step 3. Use the definition of the floor function. If the floor of a number equals an integer, I, then I is less than or equal to a, and strictly less than I plus 1. Since the floor of x squared is 9, we get the inequality 9, less than or equal to x squared, strictly less than 10. Step 4. Take square roots. The square root of x squared is the absolute value of x. So we obtain 3 less than or equal to the absolute value of x, strictly less than the square root of 10. Step 5. Split the absolute value inequality into 2x intervals. From the upper bound, we have negative square root of 10 less than x, and x is less than positive square root of 10. From the lower bound, either x is greater than or equal to 3, or x is less than or equal to negative 3. Combining both conditions gives two solution pieces, from negative square root of 10 to negative 3, including negative 3, and from 3, including 3, up to square root of 10. Here is the example we will solve. I will read it aloud. Open bracket, 3x plus 2 times open bracket, 3x plus 3 times open bracket, 3x close bracket, close bracket, close bracket equals 81. Step 1. We will use the key property for the floor function. For any integer n, the floor of x plus n equals the floor of x plus n. Here, 3 times floor of 3x is an integer, so we can take it out of the inner bracket. Step 2. We simplify inside the parentheses. Floor of 3x is an integer, so adding 3 times floor of 3x gives 4 times floor of 3x. Then multiplying by 2 gives 8 times floor of 3x. Step 3. Because 8 times floor of 3x is an integer, we can take it out of the outer floor as well. That turns the expression into floor of 3x plus 8 times floor of 3x, which equals 81. Combine like terms to get 9 times floor of 3x equals 81. Step 4. Divide both sides by 9 to isolate the floor term. So floor of 3x equals 9. Step 5. We now use the definition of the floor function. Floor of it equals n if and only if n is less than or equal to a, and a is strictly less than n plus 1. Floor function. Floor of it equals n if and only if n is less than or equal to a, and a is strictly less than n plus 1. Here, that means 9 is less than or equal to 3x. Let's display the example and the main equation on screen. Step 1. Establish a lower bound for x. We rewrite the equation to complete the square. Because a square is always non-negative, we conclude that floor of x is at least negative 1, which implies x is at least negative 1. Step 2. Establish an upper bound for x. For x at least 2, x to the fourth grows faster than 2x squared plus x, and floor of x is at most x. Therefore, for x at least 2, x to the fourth is strictly greater than 2x squared plus floor of x, which contradicts the equation. So, we only need to check the interval from negative 1 to 2. Step 3. Analyze case 1. On the interval from negative 1 up to 0, the floor of x equals negative 1. Substitute that into the equation and solve. We get x equals plus or minus 1, and within this interval, only x equals negative 1 is valid. Step 4. Analyze case 2. On the interval from 0 up to 1, the floor of x equals 0. Substitute and solve the equation. The solutions are x equals 0 and plus or minus square root of 2, but within this interval, only x equals 0 is valid. Step 5. Analyze case 3. On the interval from 1 up to 2, the floor of x equals 1. Substitute and solve. Let u equal x squared. Then u squared minus 2, u minus 1 equals 0. Giving solutions u equals 1 minus square root of 2, and u equals 1 plus square root of 2. Since u is x squared, and must be positive, we take u equals 1 plus u is x squared, and must be positive, we take u equals 1 plus square root of 2. So x equals the square root of 1 plus square root of 2, which lies between 1 and 2. Finally, we combine all valid solutions from the three cases. The solution set is negative 1, 0, and the square root of 1 plus square root of 2. In this lesson, we will solve the equation open bracket x close bracket squared equals 4. where open bracket x close bracket denotes the greatest integer, also called the floor of x. We'll follow a simple 4-step algorithm with clear visuals and checkpoints. Step 1, use substitution. Let y equal the floor of x. Then open bracket x close bracket squared equals 4 becomes y squared equals 4. Solving that gives y equals plus or minus 2. These are the only possible values for the floor of x. Step 2, handle the case y equals 2. That means the floor of x equals 2. By the definition of the floor function, floor of x equals n if and only if n is less than or equal to x, and x is less than n plus 1. So here, 2 is less than or equal to x, and x is less than 3. Let's show that interval on a number line with a closed endpoint at 2 and an open endpoint at 3. Step 3, handle the case y equals negative 2. That gives floor of x equals negative 2, which translates to negative 2 is less than or equal to x, and x is less than negative 1. We'll add that interval on the same number line with a closed endpoint at negative 2 and an open endpoint at negative 1. For intuition, pick a sample on each interval. If x equals 2.7, then its floor is 2 and the square is 4. If x equals negative 1.2, then its floor is negative 2 and the square is again 4. So both intervals work perfectly. Step 4, combine the two solution sets. The final solution set for x is the union of the intervals negative 2 to negative 1, including negative 2 but not negative 1, together with 2 to 3, including 2 but not 3. In this lesson, we will solve a floor function equation step by step and visualize every inequality on a number line for intuition. Example, we want to solve the equation, the floor of x squared minus 5x plus 6 equals 1. The square brackets indicate the floor function. Step 1, because 6 is an integer, we can separate it from the floor. Move 6 to the right side. So the floor of x squared minus 5x equals negative 5. Step 2, use the definition of the floor function. If the floor equals negative 5, then negative 5 is less than or equal to the expression, and the expression is strictly less than negative 4. We split this into two inequalities. Step 3, solve inequality 1 by finding the roots of the quadratic. 4x squared minus 5x plus 5 equals 0. The roots are 5 minus square root 5 over 2 and 5 plus square root 5 over 2. Because the leading coefficient is positive and we want greater than or equal to 0, we take the outside intervals. Step 4, factor the second quadratic. X squared minus 5x plus 4 equals x minus 1 times x minus 4. For a product to be negative, x must lie strictly between 1 and 4. Step 5, now intersect the two solutions. Intersecting the outside set with the open interval from 1 to 4 gives two pieces. From 1 to 5 minus square root 5 over 2, and from 5 plus square root 5 over 2 to 4. Recap. Example, we will solve the equation, floor of x squared minus x plus 4 equals 2. We'll go step by step, using the floor function definition to turn this into inequalities, solve each inequality, and then intersect the results. Step 1, the floor definition. If floor of u equals n, then n is less than or equal to u and u is less than n plus 1. Applying this with u equals x squared minus x plus 4 and n equals 2, we get 2 is less than or equal to x squared minus x plus 4 and x squared minus x plus 4 is less than 3. We can write these as two separate pieces. Part 1, x squared minus x plus 4 less than 3. Part 2, x squared minus x plus 4 greater than or equal to 2. Step 2, solve part 1. X squared minus x plus 4 less than 3 simplifies to x squared minus x plus 1 less than 0. Consider the quadratic x squared minus x plus 1. Its leading coefficient equals 1, which is positive, and its discriminant is b squared minus 4ac equals 1 minus 4 equals negative 3, which is less than 0. Because a is positive and the discriminant is negative, the quadratic is always positive. That means x squared minus x plus 1 can never be less than 0. Therefore, part 1 has no solutions. Step 3, solve part 2. X squared minus x plus 4 greater than or equal to 2 becomes x squared minus x plus 2 greater than or equal to 0. Again, check the discriminant. b squared minus 4ac equals 1 minus 8 equals -7, which is less than 0, with it equals 1 greater than 0. So the quadratic is always positive, which means it is always at least 0. Therefore, part 2 is true for all real numbers. Step 4. Intersect the solution sets. Part 1 gave the empty set, and part 2 gave all real numbers. The intersection of the empty set with all real numbers is still the empty set, so the equation has no real solutions. Step 1. Rearrange to isolate the floor term, then set floor of x equal to n, where n is an integer. Because x squared plus 7 is strictly positive, 8n must be positive, so n is greater than 0. Step 2. Use the definition of the floor function. If floor of x equals n, then n is less than or equal to x, and x is strictly less than n plus 1. Since n is positive, squaring preserves order. N squared is less than or equal to x squared, and x squared is less than n plus 1 squared. Add 7 across the inequality to match x squared plus 7. Now substitute x squared plus 7 equals 8n to get bounds purely in terms of n. Step 3. Solve the pair of inequalities. First, n squared minus 8n plus 7 is less than or equal to 0, which factors as n minus 1 times n minus 7. That gives 1 minus 7. That gives 1 is less than or equal to n, and n is less than or equal to 7. Second, n squared minus 6n plus 8 is strictly greater than 0, which factors as n minus 2 times n minus 4. Thus, n is less than 2 or n is greater than 4. Intersect the two solution sets to get n in the interval from 1, inclusive, to 2, not inclusive, union the interval from 4, not inclusive, to 7, inclusive. As integers, that means n equals 1, 5, 6, or 7. Step 4. Compute x from x squared equals 8n minus 7 for each allowed n, and verify that floor of x equals n. First, n equals 1. Then, n equals 5. Next, n equals 6. Finally, n equals 7. Collect the valid x values where floor of x equals n. These are x equals 1, square root of 33, square root of 41, and 7. N equals 5. Next, n equals 6. Finally, n equals 7. Collect the valid x values where floor of x equals n. These are x equals 1, square root of 33, square root of 41, and 7. X values where floor of x equals n. These are x equals 1, square root of 33, square root of 41, and 7. In this lesson, we will solve the equation x squared minus 4 times the floor of x plus 3 equals 0. We'll follow a clean step-by-step plan. Rearrange, bound using the floor property, solve for n, and then find the x values that satisfy the original floor condition. Step 1. Isolate the floor term. Move the minus 4 floor of x to the other side. That gives x squared plus 3 equals 4 times the floor of x. Now, let the floor of x be equal to n, where n is an integer. Since x squared plus 3 is strictly positive, for n must be positive, so n must be greater than 0. Step 2. Use the definition of the floor function. If the floor of x is n, then n is less than or equal to x, and x is less than n plus 1. Because n is positive, we can square the inequalities safely and preserve the order. N squared is less than or equal to x squared, which is less than the square of n plus 1. Now add 3 to all parts to match the left side x squared plus 3. This yields n squared plus 3 is less than or equal to x squared plus 3, which is less than n squared plus 2n plus 4. Step 3. Substitute x squared plus 3 equals 4n into the bounds. We get n squared plus 3 is less than or equal to 4n, which is less than n squared plus 2n plus 4. From the left inequality, n squared minus 4n plus 3 is less than or equal to 0, which factors as n minus 1 times n minus 3 less than or equal to 0. That gives 1 less than or equal to n less than or equal to 3. From the right inequality, n squared minus 2n plus 4 is strictly positive for all real n because its discriminant is negative. Taking the intersection, n must be 1, 2, or 3. To see the structure, Here is the graph of y equals x squared plus 3 in green. We'll draw the horizontal lines y equals 4n for n equals 1, 2, and 3, and mark their intersections with the parabola. Later, we'll apply the floor condition to keep the valid x values. Step 4. Compute x from x squared plus 3 equals 4n, and check that the floor of x equals n. For n equals 1, x squared equals 1, so x equals plus or minus 1. Only x equals 1 works because the floor of 1 is 1, while the floor of negative 1 is negative 1. For n equals 2, x squared equals 5. So x equals plus or minus the square root of 5. We keep only the positive root because the floor of the square root of 5 is 2, while the floor of the negative square root of 5 is negative 3. For n equals 3, x squared equals 9, so x equals plus or minus 3. We keep only x equals 3 because the floor of 3 is 3, whereas the floor of negative 3 is negative 3. Therefore, the solution set is x equals 1, x equals the square root of 5, and x equals 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.